So today we'll begin our first class on motion and geometry based methods in computer vision. So before I continue with the class, just a few instructions. Uh, if my voice is not audible or if it's getting cut in between, if it's not audible enough for you, please let me know. You can unmute your mic and let me know anytime. And another thing is, if you have any doubts, you can immediately unmute your mic and ask me the doubts. Okay, you need not wait till the end of the lecture class to ask any doubts which are related to the topic which is being discussed. And if you have any general doubts, we can have it after the lecture class or even offline. Okay, so let's begin with the course. So first, what we'll do is, according to the course plan, the first lecture class is on Introduction to Affine and Projective Transformation and Geometry. But before that, we'll just, yes, is my audio clear?
Yes,
Am
ma'am.
I audible?
Yes, ma'am.
Okay, okay. Okay, so first we'll learn about image formation, image filters, convolution filters, and about image frequency, the different filters in the frequency domain, and then we'll move back to affine and a projective transformation before going with image registration. Okay, so that means I'm taking the lecture class on image filters and convolution first, and then we will go to affine and geometry. So just shuffling that. So I'll modify that in the course plan and upload it later, the modified course plan once again. Okay, so beginning with our class. So first of all, let's have a clear understanding about the human visual system. Okay, so here this is a very abstract idea showing an illustration of how the human visual system works. Let me take the pointer. Okay, so here you can represent the human eye this way, and this one is the image lens. Okay, let's assume this is the image lens over here, and this one as the image plane. Basically, it's the retina. So what happens is, how is the image basically formed using the human visual system? So if this is the image, the light rays which passes through the image passes through the point over here. So this particular point in the lens, you can call it as the lens aperture, right? Or if it's a pinhole camera, you can assume this as the pinhole. So it passes through this and forms an image in the retina or the image plane. Now the image which has been formed would be an inverted image in the image plane. So the same concept is being used when you're trying to acquire an image, or when you're trying to capture an image using the camera. So let's say the simplest form of the camera is a pinhole camera. So if you're assuming this to be an equivalent pinhole camera, you have a pinhole and you have an inverted image formed at the image plane. And what we do is, we can assume that there is another virtual plane uh, at the same distance as that of the image plane. So let's say the image plane is from the pinhole, it is at a certain distance away from that. You can assume a virtual plane to be present or to be placed at the same distance from the image, from the lens or the pinhole over here, and that particular virtual plane will show the actual image, in the sense the inverted form of this inverted image can be formed in the virtual plane. So and that can be assumed we can assume that to be the image with which we work on further. Okay, so this is a very basic illustration of the human visual system. We'll be dealing with the pinhole camera and the working of the pinhole camera, and about the images, the different coordinates used in the images, and basically the projective geometry later on. Okay, so coming to again the visual perception. So if you look at this particular image, what we see is you have a very dark gray level or a gray level intensity or a gray level value here. And then here it kind of brightens up and you have a brighter or a lighter gray intensity value here. Right. So when we have a look at this particular image, this varying intensity levels, gray level intensity levels, what we see is that we kind of feel a very sharp transition over here. Okay, so if we try to plot that, it would look something like this. So the actual intensity, it's just an abrupt transition from one level to the other. But when it is being perceived, when the intensity is being perceived, what we see is at the edges, we kind of feel that it grows darker and then suddenly lighter and then becomes constant, right? Again, you'll see there's an undershoot, an overshoot, and then the intensity level. So the same thing can be perceived here, especially at these borders over here. If you look very closely, you'll see that at just before the border, you'll see as if there is a darker gray level, and then there is a sharp overshoot, and you see at the border as if there is a lighter gray intensity, and then it kind of reduces and then becomes a uniform color, right? So this is one kind of aspect when it comes to visual perception, when you're perceiving an image, or when you're perceiving different intensity values using the human eye. And this kind of effect is called as the match band effect. Okay. Now, another effect you must be very familiar with is here. If you observe in these three images, the inner square is actually having the same gray intensity values. Okay, so if you try to find out what exactly is the intensity value, you'll see that these three inner squares are having exactly the same intensity value. But when we look at this picture, what we see is that the human eye perceives it in such a way that we feel this inner gray color in this inner square is lighter in color as when compared to this inner square over here. We feel that this is kind of having a darker gray level as compared to this square as well as this inner square, right? So this is again one of the human visual perception concept. So this is because of the background intensity that you have. So when there is a gray level, so in this particular image you have the inner square with a particular gray intensity value, and you have a background which is completely black, right? So it kind of gives us a perception that this is much more lighter, right? Because the background actually helps with this particular perception of this being brighter, having a brighter gray intensity value. But when you look at this particular image, since the background has a very light gray level intensity, the human visual perception or the human visual system perceives this as having a darker gray intensity values as compared to these two images. So it's basically the background intensity values that is causing this kind of effect. Okay. Okay, so having said about the human visual system, let's quickly look at the camera. Okay, so we are not going to go in detail about the camera system now, just to familiarize yourself with what are the different units which are present inside a camera. So you have the optics and the aperture and the shutter in a camera body. So here, depending upon what is the aperture or the shutter characteristics, the contrast or the brightness level, etc., in an image, okay, or how sharpened the image, etc., that would change, right? Now, after that, it goes through a sensor. So you have an image sensor and a gain and an A to D. Basically, it's a analog to digital converter, right? So we'll be discussing more about sensors and how the sampling and quantization works later. So once this is over, what you have is a raw image. right? So the raw image in some systems that can go through further processing, such as, for example, demosaic or sharpening the edges, right? Or white balance where the noise is being compensated. Then there's a gamma correction where the intensity values are being compensated, and then compression, that is in order to reduce the storage values or storage required. And finally you'll get a JPEG image. Okay, basically as an example, a JPEG image where it's a it could be a lossy or lossless compression. In this case here you have a lossless compression JPEG image. So these are some of the components that you need to know, what happens inside the camera. So we'll just quickly discuss about the image sensor and about quantizing, and before going further into various image processing techniques. Okay, coming to the image formation model. So here in this image, what you see is a single sensing element. Okay, so once you have the light energy falling onto the sensor, there is a filter, and below that you have the sensing material, right? So whatever is being sensed here, it outputs this as an output voltage, right? And this particular signal then goes through or goes to an analog to digital converter to convert it into discretized values, right? Now this is one single sensing element, and this sensing element can be grouped together in the form of, or it can be arranged together in the form of a line sensor, or it can be arranged in the form of an array sensor, okay, as you see over here. And these together are, if it's a line sensor, that would be the image sensor which is used. Okay, like for example, in if you're trying to capture the satellite images, or from the geo satellite, if you're trying to capture a particular image in the ground, one of the techniques that they use is this line sensor, and they kind of do a raster scan and so on to find or to capture the images line by line. So that goes on. Now if it's an array, the whole array image sensor can be used to capture the whole image as such. And there's also another kind of sensor where it could be a circular sensor where it kind of rotates, okay, and each time it rotates, the sensing elements would capture the image. So you have different types of arrangements for the sensing elements. So finally, what you have is the image which has been formed. So the example which I told, where you have a circular sensor, is this one. So the best example what you can think of is the CT scanner, okay, where a patient is being let's say this is a patient over here, and this is the object which has to be scanned, okay, and then you have a source, a light source, okay, it could be an X-ray source if it's a case of a CT scan, and then around this circular, what you see or what you have is the sensing element, okay. So whatever is being the rays which are being here, it would be sensed accordingly, and here this X-ray source, it would be rotated around. So what you see is that at each angle over here, you will get a particular projection of the particular 3D object, okay. And then finally, these all are processed together to get the 3D image, okay. And there are various image reconstruction algorithms which are present for this. So this is just one example of a circular sensor. Okay, so let's say you have this is the particular scene or the object that has to be imaged, okay, and so you have an imaging system, and the light rays that passes through the imaging system, and you have an image that is formed. So if you look at the image plane which is present inside the imaging system, this is the particular object or the image of the object that has been captured, right? Now again, if you look at this image which has been created, you see that there is a varying degree of gray level values, right? You have dark gray pixels over here, you have light gray pixels over here, right? And you also see that this is a continuous function. So what is done next is sampling and quantizing technique is done in order to convert this into a digital image. So when you're converting or digitizing an image, this is how it's going to look like. Okay, that means it is divided in such a way that you have certain rows and columns. Okay, and each element or each cell that you see over here is called as a pixel. Okay, it's called as an image pixel, and each image pixel is given a specific intensity value to represent the image. And so as we see here, the lighter pixels or the brighter pixels come here, and as you see here also, you have the brighter pixels. Here you have very dark gray pixels, and that comes over here, right, and along the boundary too. So this is an example of how the digitized image would look like. So basically what you're doing is you're just trying to sample the given continuous signal, just like how you do the sampling for a one dimensional signal. So same way, just imagine this is a 2D signal, right? So you take samples in the spatial domain. In this case, it's not a time domain, it's a spatial domain, right? So you take samples along the spatial domain, and at each of the samples you will give a particular quantized intensity value. So how many quantized values should be used, or should be what are the quantized levels from which we can choose? That would depend upon what is the, or how much of information do we require to be retained in that particular image. So the more quantized levels you have, the more information it will contain. Okay, so for example, if I look at this image, and let's say this image is being represented by only, let's say, four quantization values or intensity values, then what happens is some of the very similar looking gray pixels with not much of values in between, okay, those would be quantized to one particular intensity level, right? So the details which are present in the image reduces when you're using lesser number of quantization levels. So the more details you require, the more quantization levels you can use. But again, that would require more number of bits to represent those quantization levels. Therefore, the storage also increases. So taking into consideration both the factor, the storage as well as the details required, you can choose, or not you can choose, like the imaging system can be configured in order to capture such an information, or you can vary the quantization in such a manner. Okay, so an image, you can represent the image in the form of, or it can be denoted as f of xy, where x and y are called as the spatial coordinates. Okay, and f is basically the image that you have, right? So these values f of xy, you can represent the image in the form of a matrix, okay, where each of the matrix elements would specify what is the intensity value of each of the pixels which are present in the image, right? So when you're trying to compute or make any kind of changes, when you're trying to process the image later, what you do is a set of matrix computations. Okay, so each of the pixel values or intensity values present, that would be represented as an element of a matrix, right? So you can represent it as this way, f of xy. And the values of f of xy is generally a positive scalar quantity. Okay, and depending upon what is the kind of image that is being created, the values would change over here, right? So usually the more the intensity of the rays, okay, it can be light rays, it can be x-rays or infrared, whatever is the system or the sensor which is being used, depending upon the amount of energy that is being received, it will have higher value. So the more the energy, the higher would be the value which is present in the particular or which has been captured by the particular image, right? Now, coming to monochromatic images or grayscale images, what do you mean by a grayscale image? So, okay, let me ask you a question. Can anyone tell me what do you mean by a grayscale image?
8-bit image.
Okay, I heard 8-bit image. Can you elaborate on that?
So basically, in binary, every cell will have 8 bits to represent the value. So 2 to the power 8, that the intensity values will range from 0 to 255.
Okay, I'll just modify that answer. In a binary image, when I say binary image, usually it has only two intensity values, which are 0 and 1, or black pixels and white pixels. That is what I usually call as a binary image. Now, binary image is a special case of grayscale image. Okay, so if I say in general, what is a grayscale image? What it means is an image which has a range of gray intensity or gray scale intensity values. That means you have varying degrees of gray color. So it can range from black, which would be represented as an intensity value of 0, ranging to dark gray values, then to lighter or brighter gray values, and then finally reaching white, where white would be the maximum intensity value. That is one thing about grayscale images. So what you saw in the previous example over here, this can be called as a grayscale image, because what you have is different varying degrees of gray intensity values over here, right? Now, so grayscale images can also be called as a monochromatic image. So monochromatic image, the word monochromatic means it also can be called as achromatic. So that means it is devoid of color. So here we are not, there is no specific color as such. All that, or the whole image is having only some gray values or grayscale values. Okay, so that is what you basically mean by monochromatic images or grayscale images. Now, grayscale, the term grayscale means it is the range of values of these monochromatic light. Okay, and gray, there is something that you call as the grayscale intensity level. So that means how much of what is the intensity of the gray color that is present. That is basically what is the intensity of the monochromatic light which is present. Okay, so just to understand this better, you also have color images, right? So in the case of color images, you have three different channels for that. You have a separate channel, red channel, a separate green channel, as well as a separate blue channel, right? So there are three different channels for a for an RGB color image. When it comes to a grayscale image, you only have a single channel. Okay, so as you just said right now, it could be an 8-bit image. Okay, so if it is an 8-bit image, the lowest intensity value that can be obtained or that can be assigned would be 0. Okay, and the highest value which could be present is 2 raised to 8 minus 1, because it's starting from 0. So totally there would be 256 levels. But when I talk about grayscale images, it is not always restricted to 8-bit images. Okay, there could be 4-bit images, 16-bit images, 12-bit images, also. Okay, so you can have other bit images also, but usually what we deal with, or what we crosses, the usually it is always 8-bit images, but you can have other quantization levels also. So talking about quantization levels, when it comes to 8-bit images, the different intensity values it can assume are 256, right? Because it can range to 2 raised to 8. So that means the different quantization levels that can be assigned is again 256 in the case of 8-bit image. Okay, I was just elaborating on your point. We'll be discussing that later in detail also. Okay. So coming back here, yeah, so the value of the image, what the images which are formed, it can have a value from 0 to a finite value, and that finite value, what it could be, would depend upon, or what is the maximum value of that finite value will depend upon what bit image it is, okay, or what are the total number of quantization levels that can be present in a particular image. Okay, so these are some points which we have already discussed. So when I say intensity value of a pixel, what that means is in terms of metrics. Okay, as I said, an image can be written as f of x y, right? So this x and y can have different values. You can have 0 0 0 1 1 1 0 and so on. So x represents the number of rows which are present in an image, and y represents what are the number of or how many number of columns are present in a particular image. So giving a value for x and y can determine what is the pixel present at this particular row, this particular column. Like for example, if I say f of 2 comma 3, what it means is I'm referring to the pixel which is present in the second row or third column, okay, if it is 2 comma 3. And if I say that f of 2 comma 3 is equal to some particular value, then that value is the actual value which is present in the particular pixel location. Okay, so that is about the use of this term. And the value of this, so this is, as I said, in the pixel, what value is present, the value of each pixel can be called as a gray level intensity, right? And this gray level intensity can vary from a minimum value to a maximum value. So let me represent this minimum value as L min and the maximum value as L max, right? So this L min, the element can go up to 0, and L max will always be a finite number. And as I said, this L min and L max, the values would depend upon how many bit image it is. So if it is an 8-bit image, the minimum value of the intensity that it can assume is 0, and the maximum value is 2 raised to 8 minus 1, which is 255. 0 to 255. Totally there are 256 intensity levels, right? So this interval is what you call as grayscale. Okay, this is something which I've already discussed. So basically, grayscale images means it is intermediate shades of gray which is varying from black to 0, where black is assigned the value 0, white is assigned the value L minus 1, depending upon what is the bit image, k bit image. Okay, so discussing about the sampling and quantization technique in the form of an illustration. So let's say this is the image that we are considering. Okay, so in this particular image, I'm drawing a line AB, and along this line, I'm trying to draw what are the intensity values present. Okay, I'm just trying to plot that. So if I plot that, what I'll get is, so here it's all, the background is white, right? So I'll get white color when I start from A. So what I see here is white. Then what happens is at the at the border, it becomes, is there a doubt? Okay, so at the border, what happens is it assumes a dark gray intensity value. So then this dips and it gets a dark gray intensity value. Now this dark gray intensity value, it kind of lightens, okay, or brightens. So towards here, it is lighter gray values. So that's what you see here. It kind of increases, you get lighter intensity values. And then again, as you go on, again it becomes darker and darker till the border. So again it becomes darker till the border, and at the border what happens is, again you have white pixels, right? So it increases here and you get white pixels. So this kind of a plot is what you call as an intensity line profile of an image. So given any line in an image, you can plot this kind of an intensity line profile. And this gives us an information of how the pixel values vary within that particular line. So in this particular line, let's say we have observed it this way. And what you see is that this is a continuous value. This is a continuous image with continuous values, right? Now, when you're trying to sample that, what happens is, so along this spatial domain, so this is basically the spatial domain over here, right? So we're considering only one single row over here. So along this spatial domain, you can sample it this way. So you can give some equidistant number of samples, okay? And at those specific samples now, if I can, plot what is these blue colored dots are, corresponding values at those particular samples, okay? So that means after doing a sampling, I'm concerned only with what are the values which are present at these blue dots, okay? So that is the only thing which I'm going to store now, or in my image those are the only values which are going to be present. I'm going to discard all the others. So now I have these samples, right? Now, after doing a sampling, you do a quantization. So what quantization means is, given a particular grayscale intensity values, and depending upon what is the k-bit image you want, okay? If it's an 8-bit image, you'll have 256 values here. Or if it's, let's say, a smaller value, let's say it's a 4-bit image, then you have 2 raised to 4 intensity values over here. So depending upon how many intensity values are required, so these are the intensity, which could be assigned, or to which these particular blue point values should be assigned. So depending on which it is closest to or where it falls within this bin in the quantization level, these are arranged accordingly. So what you see here in this particular image is after quantization. So you see that here, although there is a slight variation, okay, it here also there's a slight variation. It falls within the same bin, and so you see that now it has been quantized to one single value here, okay? Similarly, this range also, even though there is a variation, it has been quantized to one single value, and so you see it here, okay? So this is the image, okay? Also this particular line intensity profile, after sampling and quantization, what you get is this. Okay, so this is just the one-dimensional representation. When it comes to two-dimensional, it would be represented, or it would be taken in the 2D form. Okay, so the sampling would be done in 2D, and then for each of those pixels, the quantization is done. So as you see in this particular image, if you try to compare this image with this intensity profile, quantized intensity profile, with the actual intensity profile, what you see is that it is not an exact faithful representation, because here these details are lost, right? This particular peak you have here is lost in this case. So one way you can increase this is by increasing the quantization level. So that is why we say that in order to capture more details present in an image, increasing, you need to have higher number of quantization levels over here to capture all the finer details. Okay, so that's about sampling and quantization. So once the images are sampled and quantized, what you get is would be a digital image, right? And this particular digital image could be expressed in terms of a matrix form, and in terms of pixels, right? So pixels can be thought of as I said, different elements of the matrix. So the same image, I'm just taking the same image, when we're doing a 2D sampling and quantization, you can assume the pixels to be present in such a form, and then after quantization and sampling, this would be an image that is formed. Again, if we have the pixel resolution or the image resolution to be lesser, you'll see accordingly the image details would also change. Okay, so let's say after getting the digital image, you have m rows and n columns. How that can be represented is as shown over here, right? So this particular axis is the y-axis, and this particular axis is the x-axis when we are talking about the image. If we are talking about the image coordinates or an image, always the origin is over here at the top left corner, and you have the y-axis here and the x-axis here. Okay, so x-axis represents the rows, which row of the image, and y represents the column, the corresponding column in an image. Okay, so if I write f of xy, where you have m rows and n columns, right? So along x you will have from 0 to m minus 1 in the representation, and for y the representation would be from 0 to n minus 1, right? Because you have n columns over here. So each the value present at each of these dots over here can be called as the pixel values. So when you write this in the matrix form, this is how it looks like. You have f00, f01. So when I say f01, that means along the first row, this row, the second pixel in the sense, this is the first pixel, this is the second pixel. So this would be the point f01 and so on. So the last element that you will have here in this matrix would be f m minus 1 n minus 1, right? Because the last row is m minus 1 and the last column is n minus 1. So the last element you will have here, last element in the sense, the element which is present at the bottom rightmost end would be f m minus 1 n minus 1. So this is how you represent an image. Okay, now just to make you understand this better on how we can represent digital images, so just consider this image over here. Okay, so what you see is this is basically the image coordinates which with y here and the axis x here and the origin is over here. Now this particular image, if you see, the border has got black pixels, and then you have a lighter gray intensity value here, and then this particular character D, along the character D the value which you have is white, right? So if you kind of normalize the values here, what you can represent black with 0, white with 1, and let's say these gray intensity values is 0.5. Okay, so in that case, if I try to plot what is the, or if I try to write this particular circular region in terms of a matrix form, this is how it would look like. So at the origin you have 0 because it's black, so I have zeros, and let's say I have a few rows and columns of zeros over here, right? After that, what you have is gray intensity values. Let's say the value is 0.5, so I have a set of 0.5 values here, and along the letter D, okay, I have white pixels, so that can be represented as 1, right? And then again, as it goes further, you have gray intensity values, so that is represented by 0.5. Okay, so this is how the intensity values can be written in the what matrix form. And if you try to visualize this in a 3D form, okay, 3D form where each of these intensity values assumes a particular height, you can think of it or visualize this picture in this way. Okay, so here the black pixels has got the lowest intensity value, so therefore the lowest height, as we see over here. Then the white pixels has got the maximum intensity values and therefore the maximum height, and as we see over here, and all the rest remaining ones are gray pixels which are somewhere in between, and so you have here. So this kind of a view, what you can say or what you can call it, is the 3D topological representation of the intensity values. Okay, you're just trying to think of or visualize this in the 3D form, and this is how the quantized values would also be looking like. So since you have only 3 different values or gray intensity values which is presented in this particular image, here also you see that there are only 3 different levels that you see here. Okay, going further about the origin. So as I said, the origin of an image is assumed to be at the top left corner. So as you see over here, and Y represents the columns and X represents the rows which are present in an image, right? So if you have to calculate the center of an image, what you do is usually you take m by 2 and n by 2 in order to get the center of the image. Okay, so this is the concept which I've which I already told earlier. So let's say L is the number of discrete intensity levels which are present in a particular image. Okay, so it is typically an integer power of 2. So it is 2 raised to k. So as an example which I took earlier, so let's say the value of k is 8, then that means it is an 8-bit image, and the total number of values which this or intensity levels which that particular image could have is 2 raised to k, which is equal to 2 raised to 8, which is basically 256 levels, right? And all these values, that is from 0 to L minus 1, can be called as the dynamic range of an image, right? So the dynamic range of an image is determined by what is the k-bit image, what is the value of k in a k-bit image. So if you have, let's say, a 4-bit image or a 2-bit image or a 1-bit image, again, the dynamic range decreases because you have only a smaller number of quantization levels to represent that particular image, right? And this dynamic range of an image is also related with the contrast of an image. So if you have a high contrast, so can anyone tell me, you must be familiar with the term contrast. Can anyone tell me what do you mean by image contrast? Or when I say a high contrast image, what does it mean? High contrast versus low contrast. Anyone?
So high contrast means that there is a sharp difference between the values of neighboring pixels.
Yes, very good. Yes. So when I say high contrast image, what it means is when I'm looking at a particular image, I'm able to discern, or I'm able to identify the different changes in the gray intensity values properly, because there is a greater difference between a particular intensity value as compared to its neighbors. Okay, so when there is a high contrast, what happens is the details which are present in an image also becomes better. Okay, and you can have the possibility for a high contrast exist when you have a larger dynamic range within a particular image. So we'll just look at some examples. If I look at this particular example here, okay, let me ask one of you. Can anyone tell me, you can see the image, the pointer over here, right? In this particular image, can anyone tell me how many intensity values do you see here, or how many colors do you see here? Two. Yeah, there are two intensity values. Basically, you have a white color as well as a black color, right? So can you tell me how many bit image is it? So all images can be represented as a k-bit image. What do you think the value of k is in this particular image for a k-bit image with two intensity values?
1.
It's a 1-bit image, right? Okay, good. Now, here in this image, what you see is, as written over here, there are 4 intensity values. That means this is a 2-bit image, right? So 2 raised to 2, there are 4 intensity values in this image. Okay. If I compare this image with the black and white image, what I see is there is a little bit more of details that can be discerned, because there is 4 different quantization levels which can be used to represent this image. Now, as I increase the quantization level, so if I go to 8 intensity values over here, you see that more details can be understood from this image. And again, if I go with 16 intensity values, again there are more details. Okay, but this is not enough because this is a medical image, right? So and therefore usually in medical images it goes with 8-bit or 16-bit images. So the more the takeaway you have here is the more the intensity levels which are present in a particular image, the more would be the details it is able to capture within the image. Okay, and another point which you need to remember is the relation between the intensity levels present in an image and the k-bit image. So given a k-bit image, you can find out what is the intensity levels which are present, and more the intensity levels, you can say more the dynamic range which is present in the image, and more the contrast which can be obtained within a particular image. Okay, going further. So if you look at this particular image, okay, what you see is you don't see very you don't see white pixels in here. Okay, there may be black pixels but very less. What you see is more of gray values, right? Or it gives out a washed out appearance. Okay, so this is an example of a low contrast image where if you look at a particular pixel value and its surroundings, you don't see much of a difference. There is a difference, okay, but it's not large enough as compared to this particular image. So when I after doing a contrast enhancement on this image, what I get is this image, right? So in this image it is basically a high contrast image. And what do you mean by high contrast is that the if you look at a particular pixel and its neighbors, there is a large difference between the gray intensity values which are present. Okay, and one another way that you can explain this is in a washed out image, the washed out or any images that gives a washed out appearance, it does not make use of the full dynamic range. Okay, that means, for example, if you have a 0 to 255 intensity level image or an 8-bit image, okay, uh, let's say this is an 8-bit image. Clearly from this image what we can say is that it does not make use of all the values which could be attained between 0 to 255. Okay, definitely most of the values are present somewhere in between, but it is not stretched within the whole dynamic range. So when you have an image which can take any values from 0 to 254 or 255, right? uh, the way that we can enhance the contrast, okay, the first and the simplest way would be to expand the range of the image in such a way that it coincides with the dynamic range. That means you can move the minimum value which is present in an image to 0 and the maximum value which is present in this particular image to 255. If it's an 8-bit image, to get this kind of an image. Okay, so basically when you have a larger dynamic range, what happens is the contrast of the image also improves. And this can be explained with the help of histogram. So let's look at what is a histogram. Does anyone know what is a histogram? Can anyone tell me if you're familiar with the concept of a histogram in the context of image processing?
So it's basically, I think, number of pixels with respect to one particular intensity level.
Yes, very good.
More of a frequency graph.
Yes, the frequency or the number of pixels which are present for a particular intensity value. Good. So this is an example of a histogram for this particular image. So how the histogram looks like is, so let's say it is an 8, we are considering an 8-bit image. Okay, if this is an 8-bit image, in the histogram, I can plot along the x-axis. I can give 256 values over here, or I can plot from 0 to 256. And along the y-axis, what I will have would be how many number of pixels are having that particular value. Okay, so that means if I have a pixel intensity 0 in this picture, how many pixels do I have with the pixel intensity 0? So that can be plotted over here. Again, the next value and so on. So for all the 256 intensity values, I can plot how many number of pixels are present in that particular or which falls within that particular pixel intensity value. That is what you call as a histogram. So histogram does not take into consideration the spatial location of the pixels. It only looks at what is the intensity of that pixel. It only looks at what is the intensity value and accordingly bins that. So for example, if I have black pixel over here or a black pixel over here, and at 4 different corners, all would be put in the same bin, which is corresponding to the gray level intensity 0. So that means it does not consider the spatial location of the pixels, only the intensity values. But still what you see is, by looking at the histogram of an image, we can still understand an image better. We can easily say if it is a low contrast image or a high contrast image or so. Okay, and there are different techniques by which you can modify the histogram of an image in order to get a high contrast image. Okay, so yeah, so basically that's what you call as a histogram. And for the case of an 8-bit image, you can have 256 bins over here, right? Okay, so the histogram can be represented as h of rk is equal to nk, where rk represents what is the gray level at the particular value k, and nk represents what is the number of pixels which is present for that particular intensity value rk, right? And you can also normalize the histogram. When you're normalizing the histogram, you can divide that by the total number of pixels which are present in an image, and that can be represented as p of rk, where you can also call it as a pdf, or the probability of occurrence of the gray level rk. Okay, so here you can see a few images with low contrast, high contrast, a dark image and a bright image. And you can have a look at the histogram of each of these images. And what we see is that even if the image is not given and just the histogram, you can identify that it is a dark image. Like for example, if I look at this image and this is a histogram of the image, what I see is that most of the pixels are concentrated towards the darker side. So remember that, so let us assume that this is an 8-bit image with 256 values. So that means I have from 0 to 256 over here. So it can take values from 0 to 256. However, in the histogram, it is taking only the values which are only a few range of values are being taken, and which are towards the more towards the darker side, right? So by looking at this histogram itself, I can say that this is a dark image. Okay, so dark image means the exposure, there is no proper exposure in the particular image, and the image also looks like this, towards which is towards the darker side. So in contrast, if you look at this particular image, this is a brighter image. That means if I plot the histogram, what I see is almost all the pixels are present towards the brighter side of the intensity values, right? And here also you see that this is kind of a high exposure or overexposed image, as we see over here. Okay, now why it's important to observe these is by using different techniques. So as I said before, the simplest technique would be to just stretch this particular histogram. What will happen is you will be able to get a much more higher contrast image, both in this case as well as this case. So it can help, histogram processing can help with adjusting the exposure of the image or the brightness level of the image. It can also help with improving the contrast of an image. So this is an image which we have already seen earlier, where in this particular image, it's a washed out gray-like appearance, right? And what you see is in this image, most of the intensity values of the pixels are present towards the middle region. Okay, so you do not have much intensities towards the white, black pixels as well as the white pixels, and therefore there is not much contrast. But have a look at this particular image, which is a high contrast image. If you look at the histogram of this particular image, what you see is you have kind of I won't say it's not exactly equal number of pixels, but almost uniform histogram is present here. So there's an almost uniform distribution of pixels across all the intensity values, and you do have pixels along the darker side as well as the brighter side. So this means that it makes a good use of the dynamic range which is present within the particular image, right? So this is an example of histogram and how histograms can be plotted from the image, and how we can make an analysis of the type of image by looking at the histogram. And there are different techniques, as I said, for improving that. We are not discussing that because that is beyond the scope of the syllabus right now. So having understood about what is an image, how you can represent an image, and we also discussed about what is a histogram, what do you mean by dynamic range, okay, and how the contrast, how good contrast or high contrast and low contrast images look like. Okay, next we will discuss about linear filters.
But
Okay, yes.
can you please once again explain the exact difference between dynamic range and contrast?
What is your question? Can you repeat?
What is the exact difference between
Yes.
dynamic range and contrast of an image?
Okay, okay. So dynamic range means what is the minimum value and maximum value that can be attained or assigned in a particular image. Like for example, if I have an 8-bit image, the number of quantization levels that an 8-bit image can have would be 2 raised to 8, right? So that means 256 intensity levels can be obtained. So that means if I'm plotting the values from 0, I can have from 0 to 255. So total there are 256 intensity levels. So this 0 to 255 is what I call as the dynamic range. So dynamic range means depending upon what k-bit image it is, the dynamic range would be different. Okay, so if it is, as I said, if it's a, let's say, 16-bit image, if it is a 16-bit image, the total number of intensity values it can have is 2 raised to 16, which will come to some 25536 or something. Okay, so you'll have 2 raised to 16 intensity values. Now, if I write the dynamic range, what I would say is starting from 0 to 25535, that is 2 raised to 16 minus 1, that many intensity levels it can assume. So that is what you call as the dynamic range of the particular image. Now, when I say contrast, what that means is in a particular image, what are how exactly is the distribution of the pixel intensities across the image. Okay, that is what the contrast captures. So what image contrast means is it is the difference in the intensity between the highest and lowest intensity levels which are present in an image. Okay, like for example, if I take this dark image, okay, in this dark image what I see is the highest intensity value it is having is only this particular value, right? So that means it is even if it's an 8-bit image, let's say this is 256, it is even lesser than 256 by 2, not even half of that, right? And then the lowest value you have here is not 0, it is again somewhere which is above 0, right? So what that means is the contrast here is lesser. So when I say contrast is lesser, that what that means is the maximum intensity value and the difference between the maximum intensity value which is present in an image and the minimum intensity value which is present in an image would be lesser, okay, or it would not it is lesser as compared to the dynamic range present in the particular. Dynamic range means what are the possible values it can assume, it can have, okay, or it
Yeah.
is capable of assuming, whereas it
Yes,
is
ma'am.
not there. Okay, so contrast is more like a real case where it is not there.
Yeah, ma'am.
Is it
Thank you.
clear? Okay, okay. Any other doubts so far? Okay. Fine. Moving on to filters. Now, just have a look at these two images here. Okay. So you have a zebra here and a Dalmatian here, right? So if you observe these two animals, you can assume the background to be of the same intensity or having the same background. If you just look at the two animals or the objects of interest for us in this case, both of them have got both black pixels as well as white pixels, or almost an equal number of black and white pixels in their body, right? Or in the objects, what we see is almost an equal distribution of black and white pixels. So if I try to plot a histogram of this image as well as this image, even if you look at the background, if it is kind of the same brown color over here, what you see is that the histogram may also look very similar, okay, but because the basically the intensity values which are present, the number of intensity values that it can assume would be the same, but as we see, these two are very different images, right? So in these two images, in order to make a clear distinction about what are the details which are present in this particular image, okay, or to make more sense of the difference between the two images, just plotting a histogram alone may not be sufficient. You also need to have a clear idea about what is the pattern of the pixels, or you need to consider a group of pixels and see how the pixel intensity values change. So if you look at this image, it's more like the black and white stripes, or stripes. Here what you see is more like blob like structures over here, right? So here getting information about the neighborhood of the pixels along with the pixels, okay, pixel as well as its neighborhood together would help us to give a better idea of what the image is, right? So that is where spatial filters come into play, okay. So spatial filters can be used for different kinds of applications. It need not be just to find the pattern, it can also be to smoothen noise. So let's say there is some noise in the image. If you want to reduce the noise, you can take the help of the neighborhood pixels. When I say neighborhood pixels, what I mean is if I'm considering one particular pixel, right? In order to get a better idea, or in order to filter out that particular pixel, I can consider the neighborhood. That is basically the pixels which surround that particular center pixel. Okay, so that can be used to smoothen noise or to find edges or so on. So there are different applications which can be done using the linear filtering. And we'll be going through some of those applications next. Okay, so as we see in this image, so let's say I'm considering a pixel XY. Okay, so this is the image F, and as you know, this is a y-axis, this is the x-axis, and I'm considering one single pixel XY at this particular location here, right? So when I say calculating the neighborhood, what I can do is I can take the number of pixels which are surrounding this particular pixel. So let me call this pixel of interest which we are considering as the center pixel. Okay, so surrounding this center pixel, I can assume a certain number of pixels in the neighborhood. Okay, and let's say I'm assuming that to be SXY, and the number of rows and columns in that SXY that can vary. So the simplest example you can think of is a 3 cross 3. That means just taking the pixels just surrounding the center pixel. Now, what a filter operation does is, a spatial filtering operation, what it does is, it can take a weighted average of that pixel neighborhood along with a specific mask or a kernel. okay, and then give a new value for the center pixel. So it is the mask that is, I have not drawn it here, but let's assume that there is a mask over here, right? So this particular mask, or what you call as the kernel, would decide what is the type of information, what is the type of filtered image you want. So there could be a mask, or the mask values would change if you're what you're trying to do is basically smoothen the particular image, or the values would change if what you're trying to do is finding the edge information, edge details of the image, and so on. Okay, so we'll learn more about the masks or the kernels used in the subsequent slides. For now, try to understand that let's say you have a mask or a particular kernel, right? So what it does is it basically slides through the image, right? So let's say first the kernel or the mask is kept over here, the weighted average is taken, and that particular weighted average, it could be a weighted or unweighted average, okay, depending upon the mask. So I'll just call it as average for now. The average is taken, and whatever average is obtained, that value is replaced on the center pixel here. Then what is done is this particular mask is slided to the next position, right? So let's say we are striding it by 1 pixel. So after 1 pixel striding, it goes to the next location, and again the average is taken, and that new value comes to the next corresponding position in the filtered image. So image G represents the filtered image after filtering, and this goes on. So this mask keeps on sliding. Each time it slides, it takes an average value, and the corresponding value is being stored in the center pixel here, and then this is done throughout the image till it reaches the end, and then you have the final filtered image. So that is the basic concept of how the spatial filtering works. Okay, so what you have is an image and a mask or a kernel, and this mask or kernel can have any size. So usually it is, let's say, 3 cross 3 or 5 cross 5 or so on, and then this is slided across the image to get the filtered image. So what is the average value? That value is getting stored in the filtered image. Okay, and this is an example of applying such a spatial filtering. So let's say this is an image here. This is basically an angiogram image, and in this image, let's say my aim is to smoothen the noise which are present. So I do see that there are it's not homogeneous background over here. There are some abrupt changes in the intensities, and I want to smoothen this out. So what I can do is this, a very simple mask which I can use is a box filter. So what box filter means is, box filter means a mask or a kernel. So I'm not going to call it mask from now on. I'll just call it kernel. So what it means is a kernel which has the same values throughout. Okay, so if it's a 3 cross 3 kernel, all 9 elements which are present in the 3 cross 3 kernel has the same constant value. So, okay, so that is called as a box filter. So I can use a box filter to smoothen the noise over here. So let's say I take a box filter and I take this particular area, okay, and the neighborhood, and then it will calculate what is the average value, and it replaces that over here, and slow on it goes on, it slides and it calculates the value. So what we see is in these regions where the intensity of the gray levels does not change, it does change slightly but not much, okay, it gets smoothened. So here you have kind of more of a homogeneous region over here, or very slightly varying intensity values when it comes to a filtered image, right? And then where you have the bright values, you have the bright values over here also. Okay, so this is an example of how you can smoothen out the noise which is present here, okay, using a box filter, which is also called as an average filter. Now, can anyone tell me, okay, so one advantage that you see is that the noise has been smoothened over here, right? It is smooth over here. But can you tell me any disadvantage that you see from this particular figure? Or a disadvantage of using a box filter or an average filter for smoothing noise? I'll repeat the question. Do you see any, by looking at this example, this is the original image. This is after using the, after filtering using a box filter or an average filter. What box filter and average filter means is having the same weights or having the same values within the kernel. Okay, so need not worry about that. Just look at these two images, and can you tell me what disadvantage, do you see any limitation or disadvantage in the filtered image as compared to the original one?
High contrast to contrast conversion.
Uh, okay. Okay.
Excuse me,
So
ma'am.
yes.
Yes. So, am I audible?
Yes. Yes. Tell me.
Yeah. So I guess the edges become smooth as well. So the detection of whatever we are trying to detect becomes difficult.
Yes, yes. Okay, so all of your answers are pointing to the same thing. Like one of you had talked about the contrast, the resolution, and so it all points to the same thing. So as you said, what happens is while smoothing out all the noises which are present in the background, the edges are also being smoothened. So what happens is the edge details becomes, the edges also get blurred. Okay, so in some cases, now again the applications may vary, right? In some cases we may have to preserve the edge details because maybe let's say our aim is to kind of find out what is the area or segment out this particular I don't know, this particular organ over here. Okay, or it may be to find out the area after segmenting this particular organ. So in such cases the edges play a very important role. Okay, and what happens is that if you're simply using an average filter, as you see in this particular image, even though it helps with smoothing out the or smoothing the noise which is present in the background, what happens is the edges are also getting blurred, so which means that we are losing the edge details which are present, right? So that is one disadvantage of using the average filter. So we'll come to that again. So this is the same explanation which I just said right now about how the linear filtering, spatial filtering is done. So instead of using the same set of weights, what we can do is we can use different set of weights. Okay, so different set of weights, as I told earlier, for different operations you can use that. So not always do we use spatial filtering for smoothing. You can use it for finding the edges, as I told, and we'll be discussing that later also. So different set of weights can be used for representing different processes in image processing. And the example which we just looked at right now is basically taking the local average, and as I said, it is the same values which are taken, right? Okay. So let's say if this was the image and what we had considered was 1 by 9. The value which we had taken was 1 by 9. Now, why we are taking a divided by 9 over here is basically we're just normalizing this particular filter. Okay, so it's basically 1, 1, 1, 1, 1, 1, 1, 1, 1. And since you have 9 elements, you're just dividing that by 9 throughout. Okay, so that you're just using a normalized kernel over here, right? And then that is being multiplied. So you take the average of those values and you get these values over here. And this is just to show an illustration of what happens, and what you get would be as seen in the particular image. It will help to smoothen out the noise, but at the same time it will also smoothen out the edges. Okay, so what we can do as to improve that, or to ensure that the edges are preserved and the edges are not blurred much, what you can do is you can do a weighted average. So within the kernel itself you can vary the weights which are given to different pixels. So if you look at the previous one, what you see is it is the same values which are given to all the elements which are present in the kernel, right? So instead what you can do is you can give a larger value to the center pixel and lesser weightage okay, to the neighboring pixels. Or if you're considering, let's say, a 5 cross 5, which is a much larger kernel, again, the inner pixels or the center pixels can be given more weightage as compared to the ones which are surrounding. So how it helps is, let's say if you have a particular edge. Okay, so at the edge, what you see is that edge pixel or the center pixel, let's say, has a very high intensity value, and the neighboring pixels, let's say, has a black value or black values, or darker gray intensity values. So that is an example of a typical edge, right, where you have a white pixel at the center and a dark pixels. Let's say not all the values have that. Let's say these three are having white regions and these are having black regions, like, just to take an example, or more. Okay, so what happens is, now when you take an average, the center pixel, instead of having a white pixel or a brighter value, it gets replaced by an averaged out, that is a gray value, right? That is how the blurring actually occurs, or that is the reason why it occurs. So if you're giving more weightage to the center pixel as compared to the neighbor pixel, what happens is, although you are averaging it, since more weightage is given to the center pixel, it will again have, even after having that weighted average, it will still have a higher intensity value. So it is an improvement over the average filter. I'll just repeat that once again. So what the improvement that you're doing is, you're basically giving a larger weight to the center pixel as compared to the neighborhood pixels, or the weights keep decreasing as the neighborhood pixels, the distance of the neighborhood pixels is far further away from the center pixel. So by this, what you're trying to achieve is, you're trying to reduce the blur which is present in the edges. Okay. And again, about linear filtering, what you see is, one property of linear filtering is that it is shift invariant. What do you mean by shift invariant is, given the same neighborhood pixels, wherever it is present in the image, it will still give the same value, right? If the neighborhood, as long as the neighborhood pixels remains the same, wherever it is present within the particular image, it will give the same value. So that's a shift invariant. And also this spatial filters, it is also linear. Linear means, if I take the sum of two images and then filter it, it would be the same as taking the sum of each of the filtered images separately. Okay, so because it satisfies both the shift invariant as well as linear properties, it can be called as a linear filtering. Okay, we'll discuss more on this in the coming slide. Again, just some definitions which we've already seen. So what kernel means, kernel of a filter means, it is basically the weights which are given. Okay, so with these weights, it is multiplied with the underlying image pixels to get the center pixel value. And convolution is basically the process of this averaging as it slides through the image, right? So let's say I have an image which is represented by FUV, and if HIJ is basically the this one, sorry, HUV is basically the mask, then RIJ is the filtered image, then I can represent it as sigma UV, that is across all the pixels, HI minus U, J minus V, FUV. Okay, so basically you're taking a convolution of the image as well as the convolution mask to get the filtered image. We'll see more on this later. Okay, so again, this is an example of how the averaging helps to smoothen the noise which are present in an image. So here you can see the same image which has been corrupted by a particular type of noise. Now, noise can be of different types. Can anyone identify what kind of noise has been added to this image? So I'll just say
Salt and
that yes,
salt and
very
pepper.
good. Yeah, it's a salt and pepper noise. Now there are different types of noise. There could be a Gaussian noise, there could be a Poisson noise, salt and pepper noise, and so on. So this is an example of a salt and pepper noise. So as the name says, what it means is there is an image, and it looks like as if some salt and pepper has been sprayed on the, or has been put on the image. Okay, so that kind of a noise is what you call as a salt and pepper noise, and the salt and pepper noise usually occurs if there is some defective imaging sensors which have been used, okay, for capturing that particular image. So that means some of these sensors do not work, and it gives either a black or a white pixel. Or sometimes it could be some random values may be added to the image during the pre-processing step or so on. So because of various reasons which are present within the imaging system, the salt and pepper noise may occur for some kind of images, and this is an example. So this is an image with lesser salt and pepper. Here it is much more salt and pepper, right? And we are trying to see how this images get smoothened by using an averaging filter. Okay, so if you assume that the pixels in the neighborhood are similar, then you see that the averaging filter would work well. Okay, so what I can do is I'm just using an averaging filter with a box filter of 5, and by taking the 5 would be at the center pixel, okay, and it's a weighted average which is taken. It could be any number, just taking a random number over here. So by taking a weighted average along the particular image, what you get would be a smoothened image. Okay, smoothened, you can call this process as either smoothing or blurring the image, because basically what you're doing is blurring off these pixel values over here, right? So what happens is now as you see, the salt and pepper noise has been reduced by using the averaging filter, a weighted averaging filter. So this is just an example. One more thing you need to note is by if you vary the size of this kernel, okay, so instead of 3 by 3, if I take 5 by 5, or let's say 15 cross 15, okay, or so, accordingly there would be changes. Can anyone tell me, if I increase the kernel size, how does it affect the smoothing or blurring? Does it increase or decrease?
It increases the smoothness.
Yes, it increases the smoothing, right? So as I increase the size of this particular kernel, the smoothing also increases. Smoothing increases, but at the same time, the edges also, at the edges, the blurring also increases. So that is something which you will have to, note while you're doing a filtering process. That means the size of the kernel which is being used has to be decided depending upon how much of smoothing or blurring is required in your particular image, or what you desired for your filtered output. Now, this is an example of using different kernel sizes. Okay, so when you're using a small kernel size, you see that there is a blurring, okay, but there is more blurring when you're using a larger kernel size. Okay, so when you're taking an unweighted average, as I said earlier, the main problem is that the edges also get smoothened out, and as you increase the size of the neighborhood also, what you see is that the smoothing and the blurring keeps increasing. Okay, and if you one way that you can reduce that is by using a weighted average. Let me just look at the time. Okay, 4 minutes. I think I'll just okay, I'll just discuss this quickly. I'll take 5 more minutes, discuss this quickly. So one example of how you can give more weightage to the center pixel as compared to the neighborhood pixel, one example is a Gaussian filter. So this is a representation of how the Gaussian distribution is like, where you have a high weightage given to the center pixels, and as the weight keeps decreasing, as the distance of the neighborhood with respect to the center pixel keeps increasing, and then you have very low weightage to the neighborhood. I mean, the neighborhood pixels which are much further away from the center pixel. Okay. And this is a type of filter is what you call as a Gaussian filter, and this is the representation. So here sigma represents what is the weight, or how much weight can be given to the center pixel or the corresponding value. So as the value of sigma increases, what happens is this spread over here also increases. Okay, and we'll just look at some examples of how it affects the image. Now, one example of a discrete approximation of a Gaussian filter is shown over here. So if you observe in this case, it's a 5 cross 5 pixel. So the centermost pixel is having the largest value or weight, which is 41. And then you have the neighbors. The neighbors which are just next to it are having values of 16 and 26, okay, which is much lesser than 41. And the pixels which are at the boundaries over here, which are much further away from the center pixel, are having even much lesser values, which are 147 and so on. Okay, so this is an example of a Gaussian filter. If you try to imagine this as intensity levels, you see that this has got the highest intensity or height, and then these reduces and these keep reducing, so giving somewhat like this kind of a shape, right? And then you're normalizing by 1 by 273. If you take the total of these values, it's 273. And if you use this particular kernel for smoothing a particular image, the advantage is these kind of Gaussian kernels would help to decrease the blurring that happens at the edges, but at the same time it gives a good amount of smoothing at the other homogeneous or smoothly varying background regions also. Let's look at an example also in the next slide. Okay, so now the value of sigma plays a very important role here. 1 minute. Okay, the value of sigma. Now, if the value of sigma is very small, so what that means is you have the weights which is concentrated towards the center pixel alone, and the neighborhood does not make much contribution towards the smoothing process. So therefore, the smoothing would be lesser, because the smoothing actually should happen with the help of the neighboring pixels as well. Right? So as you increase the size of sigma, what happens is the neighborhood pixel values also play, or they contribute towards the smoothing process. Okay, and then there is a kind of considerable smoothing that happens. Now, if you take very large value of sigma, what happens is again it will cause blurring, and the edge details would be lost, or it would again get blurred. So choosing a proper value of sigma is important when you're working with Gaussian filters. As an example, you can look at this particular set of images. So this first row are original images. So the actual image that you want is having only one intensity value. It's a homogeneous image with just one intensity value. And in these three images represent the original image with the same intensity value being corrupted with noise of varying degrees. Okay, so this sigma represents the amount of noise that has been added to this particular image. So it's basically an additive Gaussian noise. So in this image, sigma is equal to 0.05 noise is added here, more noise is added here, again 0.2, there's a lot of noise which is added. Okay, now if I'm trying to smoothen this image using a Gaussian kernel with sigma is equal to 1 pixel, this is the result which I get. If I take sigma is equal to 2 pixel, this is the result which I get. Okay, so again, depending upon how much of noise is present, choosing a value of sigma would be important. So if you look, for example, there's a lot of noise over here, sigma is equal to 1 pixel for the Gaussian filter did not really help with smoothing this particular region, but sigma is equal to 2 has helped it further, because now there are more neighborhood pixels that contribute towards the smoothing process, right? So accordingly, depending on the value of sigma, the amount of smoothing that happens also, or the amount of suppression of noise that happens within each image also varies. Okay, so we'll continue with sharpening spatial filters in the next class. If you have any doubts so far, you can ask me now.